Okay, so thanks first of all, Ariane, for this kind invitation. As you said, I'm a postdoc at Polytechnique, but I will today tell you about the sort of project that started during my PhD, which I did at SUA here at in France. And I did it in this delocalized, a bit all over the world group. And so I will tell you about something that you are really familiar with, namely neutral and charge excitations, or optical and fundamental band gaps, and how can we obtain them with Quantum Monte Carlo for, in general, periodic systems. Well, I think, first of all, I will do a very short introduction of Quantum Monte Carlo with its, well, benefits and advantages and problems. And then I will start with the fundamental or gap or charge excitation, and we'll discuss the biggest problem is the size effects, and discuss the application of this charge excitation on silicon and also on solid hydrogen. After that, I will move to discussing the optical gap, again, its size effects, and again, application to carbon and also solid hydrogen. So since I will talk quite a bit about hydrogen today, I decided to do like a little parenthesis and do a little introduction in hydrogen. So in solid hydrogen. So today I will talk about hydrogen at room temperature, so at ambient at 300 Kelvin, and in solid phase at various pressure ranges. As for the fundamental gap, I will discuss the higher pressure range, where the hydrogen is in phase 3, and this is the phase at which hydrogen metallizes at around 400 gigapascal. And in case of the optical excitations, I will focus on the lower pressure phase 1 of hydrogen. And in this phase, the experimental structure is known of hydrogen, which is a molecular H hexagonal post-Pack structure, whereas at the phase 3, so at higher pressure, this structure is not available experimentally, and we have to rely on theoretical predictions. Well, in Quantum Monte Carlo, contrary to many-body perturbation theory, we want to approximate directly the many-body wave function, the wave function of n electrons. There are various ways to do that, and here I will just focus on one of these ways, which is a Slater-Jastrow form, where we approximate the wave function as the Slater determinant, constructed usually from orbitals obtained with density functional theory, which is multiplied by the correlation factor, which approximates the correlations, which is called Jastrow. This trial wave function, we can parameterize it with the parameters, for example, some parameters, and we can write them then as the product of the determinant, shortly as the determinant, and the Jastrow factor. Here, as you see, we want to describe the wave function thermodynamic limit. However, we are limited at the few number of electrons, therefore immediately arises the problem of size effects. Okay, now having this trial wave function, we can use the variational principle and using the Monte Carlo integration, evaluate this high dimensional integral, which gives us the variational energy. Then we know that this variational energy will be always larger than the ground state energy. This allows us then to optimize our wave function, so find other set of parameters A, in order to obtain lower energy, and like this we can finally, hopefully, converge to the ground state. Of course, as you can immediately notice, this approach called, well, variational Monte Carlo is sensitive, very sensitive to the choice of the trial wave function. However, we can do better than that. And namely, we can project out the ground state from the trial wave function, doing the imaginary time projection in which if we put beta, which is imaginary time to infinity, will give us the ground state. However, and this method is called diffusion Monte Carlo. However, here we need to be careful since we have to sample the positive and negative regions of the wave function separately. Therefore, we have to approximate the nodes of the wave function, and usually we take the nodes from the Slater determinant. In this approximation called fixed node approximation. So in principle, the QMC can give us exact ground state energies, well, considering the fixed node approximation and also considering the finite size of the simulation cell. Now, if we want to study the periodic systems, we can use similarly to DFT the fact that when the electron wraps around the simulation box, it can obtain a phase. Here we call it theta, but in DFT we call them K points. Similarly, this helps us to converge to the thermodynamic limit. However, sampling different twists or phases can only cure the single electron corrections. So in practice, this phase or this K-point sampling allows us, just like in DFT, obtain the band structure. And here just I present you the band structure of hydrogen, of this C2C structure of hydrogen. This is the DFT band structure, but in QMC we can do the same, namely we choose a grid of twists, so K points, and we run independent calculations for each point, and then we can resolve the band structure. Now, this is exactly what we can do, what we do. And here is the case of the fundamental gap or charged excitation, which we obtain simply by adding and removing electrons from our system. And also we have to make sure that we keep a neutralizing background to have a neutral charge in the system. Now the gap will be defined as this energy differences. We can also define the electron addition and removal energies as a function of K point or twist, and resolve them onto the band structure, and we can see how they sort of nicely repeat the band structure of the DFT with sort of usual scissor correction that we used to from GW. Of course, we can define the indirect gap, the minimal, the indirect gap, and also the direct gap. However, here one needs to be careful because we work in QMC, we work in a supercell, so we need to make sure that we unfold the bands correctly. So now it seems that, well, it's all very simple and obvious. We just add, remove electrons and compute the energies. However, here come the problems, which are the size effects. And the long-standing question since, I think, 20 years is discussed whether the fundamental gap scales as inverse number of electrons in the system or inverse linear system size, 1 over L. This is also can be obtained as the cubic root of the number of electrons, right? And of course, the inverse number of electrons converges to thermodynamic limit way faster than the inverse linear system size, which is quite painful to converge to the thermodynamic limit. Well, a very simple argument would be that we know that the total energy scales as inverse number of electrons. Then, since to obtain the gap, the fundamental gap, we do nothing but subtracting and adding the total energies of charged and neutral systems. Probably the size corrections will cancel, and there will be no size corrections on the gap. However, one needs to be careful. Here, what we do, we, as I said, add and remove electrons and keep neutralized background. And since we do it for the periodic system, we do it for every image, effectively creating a unwanted lattice of quasi-particles. And this energy of this lattice, which is governed by the Madelung energy, needs to be subtracted from the system. And this is the main effect on the main size effect on the charge excitations. We can look at it more formally. Namely, we can look at the structure factor, and we know that for the ground state, at the vanishing momentum, the structure factor, the static structure factor, will vanish. And from the structure factor, we can write down the potential energy and also the kinetic energy, but here we'll just focus on the potential energy, okay? Then for the charge excitation, we can look at the structure factor difference between the structure factor of the charged system minus the structure factor of the neutral system. And here I'm showing you the two branches, namely the upper branch is when we add an electron and subtract the ground state, and lower branch is when we remove an electron. And this is the case of silicon for different sizes, for different supercell sizes in different color. And obviously we can see that it doesn't extrapolate to zero, which indicates that we actually have some size effects, which actually indicates that the size effects do not cancel in this for the quasi-particle energies. And in fact, we can actually show that some of these two branches extrapolated to zero can give us the inverse dielectric constant. Now, the size effect, which is just the difference between this continuous integral we want to obtain here, minus the fact that we have to evaluate this integral as the discrete sum, right? Well, times the Coulomb interaction. This term here actually is just the Madelung constant, which is just the energy of the formation of this unwanted lattice of quasi-particles. And this Madelung constant, then we can, in the leading order, multiply by the extrapolation of this structure factor alpha. Now, for the band gap, the size effect will go as the Madelung constant divided by the dielectric constant, since we have to sum the two contributions. Okay, we know that the Madelung constant scales as inverse linear system size 1 over L, which is bad news because it means that the fundamental gap convergence is very, very slow. Here we studied the convergence of the band gap of the fundamental gap of silicon, and we had to, for the small cells, we had to include beyond leading order corrections. And once we take into account them, this which is this green, the green points needs to be compared with the red ones, we see that the convergence of the green points is indeed 1 over the linear system size, or cubic root of a number of electrons. In fact, we can also, with our scheme, obtain the convergence of the gap for the smallest system. Okay, so it seems to work pretty well. Let's see what about hydrogen. However, here, in the case of hydrogen, we have to work in, we work at finite temperature, as I said, and there we have to sample the protons, right? We will do it in the Born-Oppenheimer approximation using couple electron ion Monte Carlo, which means we'll use path integral Monte Carlo for protons and quantum Monte Carlo for electrons. During the sampling, we will take 40 independent configurations. On each of these configurations, we will perform the electronic structure calculation, for example, the calculation of quasi-particle excitations, and average over the number of configurations. We can then, in the same way, project these energies onto the band structure here in orange, and in this case of hydrogen at 250 gigapascal and at well, this is 200 Kelvin actually. We see that actually the 0-point motion, so the reduction of the gap due to this 0-point motion is quite large, as 2 electron volt, which is not that surprising because hydrogen is very light and also it has a lot of quantum nature. But nevertheless, it's quite a big number. We can also study the closure of the band gap with by increasing pressure. And here we were able to discriminate one structure, which is the C2C, with respect to the other structure, CMC12. These both structures were proposed by the random structure search. And we were able to discriminate one with respect to the other by comparing two experiments. And in the experiment, they perform absorption measurements, and they obtain they fit the onset of the absorption to obtain the band gap. Okay, this seems to be that fundamental gap or charge excitations are pretty much under control in Quantum Monte Carlo. What about the neutral excitations or optical gap? Seems to be simpler, right? Because here we just need to obtain the energy of the excited state and subtract the energy of the ground state of the same neutral system of the same number of electrons. However, okay, how do we obtain the excited state? Here I just remind you that our trial wave function is the Slater-Jastrow wave function. So here in the Slater determinant D, we just promote one electron from valence to the conduction band, right? So we substitute one orbital, one valence orbital by the conduction orbital, which allows also to resolve this gap in the momentum. Seems pretty straightforward in the same way as it was for the fundamental gap. However, here again, the same question arises. How does it scale with the system size? Is it 1 over number of electrons, or is it 1 over the linear size of the system? So logically, we would say that, okay, this is a neutral excitation. We don't add any charges in the system. So our finite size effect on the excited state and the ground state should cancel, and there shouldn't be any size effects on this optical gap. However, it turns out that in the case of a single determinant excitation, and in the case where we use in this Slater orbital the delocalized or the Bloch orbitals that are delocalized, for example, for carbon, for solid, for diamond carbon, we actually obtain exactly the same results as when we obtain the quasi-particle gap. So it's the same whether we excite an electron or we add and remove electrons and look at the gap. The size effects are also similar. Here we look at again the difference of the structure factor for the excitation, and in color, and in black is what I showed previously is just the structure factor of this quasi-particle, quasi-electron, or quasi-hole, right? The two branches, and we see that the structure factor of the neutral excitation doesn't extrapolate to 0, meaning that there are size effects. And it's the same for the larger system. However, here the statistical uncertainty is larger and it's harder to converge, but clearly the colored lines do not extrapolate to 0, indicating that we have similar size effects as in charge excitations. So it actually means that when we have single determinant excitations with delocalized Bloch orbitals, our neutral and charge excitations coincide, and the size effects will be 1 over linear system size, meaning that we cannot obtain the neutral excitations with this kind of wave function. So we showed also formally that our gap will scale as the Madelung constant divided by the dielectric constant. We have also proposed a way to cure this sort of spurious size effects by subtracting the Madelung constant evaluated at the excitation length, or if you want, evaluated at the exciton length, which actually means that when our exciton fits the supercell or the simulation cell, so when it's proportional to the L, right, the two contributions will cancel and we will not have any size effect on the neutral gap. However, when our exciton extends our supercell, we will have to subtract some this unwanted size correction from the gap. Okay, another way to not to have size effects on the neutral excitation is to use multi-determinant wave function. And in this case, we have also shown it formally. We will not have size effects on the neutral excitation. So our structure factor will vanish at zero momentum. Okay, so let's see how it works in hydrogen again. Here, as I said, we will look at solid hydrogen, but at lower pressure. So phase 1, where actually, as I said, experimentalists observed the structure, which is the molecular hexagonal closed pack structure. However, here the molecules are rotating. So they are not aligned, they are rotating. And so we will again do the same procedures. So at room temperature, we use path integrals for atoms and QMC for nuclei. And we will average over the randomly independent random configurations. Here is just a snapshot of this path integral simulation. This is a supercell of 96 atoms. We indeed see that the molecules, they are rotating freely, I would say. And so the electronic structure properties will be averaged over this kind of configurations. Okay, let's see the result. No, first of all, here we also have a available inelastic X-ray scattering experiment where the authors extracted the gap with a different pressure by fitting the onset of the spectra. And for example, at low pressure, this onset is pretty steep and pretty clear that there is a gap, right? There is a gap in the system. However, at the higher pressure, the onset is kind of not exactly clear, but nevertheless, they have fitted this onset and extracted the gap and did it for various pressures, which allows us to compare. However, to understand what exactly they observe, we have also performed Bethe-Salpeter calculations in the standard form with the RPA screening, which is the screening is the same for all configurations within one density. We did G0, W0, scissor-corrected LDA bands, and we used the LDA wave functions. And then in the same way, the spectra, so in this case, it was the imaginary part of the inverse dielectric function, we averaged it over this number of configurations extracted from path integral simulations. And the same way, we average also the excitonic, the optical gap from Bethe-Salpeter and also the GW gap. Now, the results. So here I'm showing you the Quantum Monte Carlo neutral gap and the quasi-particle gap. So here the no size correction scheme was applied. So the quasi-particle gap we obtained with adding and removing electron, neutral gap just by exciting our system. We see that at high density, so at high pressure, actually the two coincide, just like we've seen for carbon. However, when we move to a lower pressure, we have the more localized Bloch states, and here we can already see how the neutral excitation deviates from the quasi-particle gap. So here we can actually talk about the sort of binding energy or the localization effect, if you want. We have also, for the lower pressure, we have also use another basis set, which is just localized atomic orbitals basis set for hydrogen molecules. And we looked at the excitations using this basis set at lower pressure, because here we know that the excitation is actually localized. And actually, these results are on top of the neutral optical gap obtained with in the plane wave basis in red here. Now let's see what our beloved Bethe-Salpeter is giving us. So it's actually pretty close to the Quantum Monte Carlo result for the neutral gap, so without size correction, except for the lowest pressure. So here we'll have to investigate further this discrepancy. Then we can also look at the GW results, and we can see nicely how the binding energy is decreasing when we increase the pressure. Also, we can look at the size-corrected quasi-particle gap, so which should be compared to the GW gap, right? Because here in red is the quasi-particle gap with fully size-corrected, so it should represent the sort of GW gap. However, it's somehow larger, but what is very interesting is that the binding energy, so the difference between the red circle and the triangle, is the same as the binding energy in the case of Bethe-Salpeter equation, and this is also true within the all pressure ranges. Okay, so it means that at low density, right, at low density, our Bloch states are localized, and our excitation, our exon fits the simulation box, so the supercell. No size effects will be needed for the neutral gap, so for this neutral optical excitation. However, at higher pressure, at higher density, the Bloch states kind of more delocalized. There will be some size effects, which we kind of roughly evaluated by evaluating the exciton extension, and we found that the exciton is twice larger than the simulation box, which means that we will have to move our triangle to correct it to add the size effects correction, which will move it by the 0.27 electron volts. Now we can look finally at the experiment, which is somewhere here. Well, we can see that at low pressure, the experiment is pretty much in agreement with our Bethe-Salpeter and QMC results. At high pressure, it seems that the experiment is more results in more the experiment extract the quasi-particle gap, and for that we can look at our Bethe-Salpeter results. Here I am showing you the on the right the Bethe-Salpeter results for the lowest pressure and for the highest pressure. So lowest pressure in green, highest pressure in blue. The experiment is dotted, and the Bethe-Salpeter spectra is solid. And here at higher energy is the deviation is due to the convergence. So once we increase the bands, this theoretical curve will approach the experimental one. But what is interesting that at lower pressure, the results, the spectra agree, and or at low energy, the spectra agree. At high pressure, so no, at sorry. In blue is the highest pressure or the lowest pressure. The lowest pressure at low pressure, so which corresponds to the 6 GPa. Here, the extracted experimental gap and the Bethe-Salpeter gap, they agree pretty well. However, at higher pressure, which is in green here, the Bethe-Salpeter gap extracted in the exciton is somehow lower than the one extracted from the experiment, which sort of indicates that this procedure of the fitting the onsets is not really reliable at high pressure. But here at high pressure, the Bethe-Salpeter result agree with QMC result, which is quite nice. So in conclusion, there are two conclusions. So for the charge excitation, so for the fundamental gap, the size effects will scale as 1 over the linear system size. Luckily, here we have a pretty robust scheme to cure the size effects, even for the smallest system. For the optical gap, in principle, the size effects should go as 1 over number of electrons. But in the case of the single determinant excitations and for the delocalized block states, this will actually coincide, the optical gap will actually coincide with the charge gap. So we will have to do the multi-determinant excitation where there will be no size effects on the neutral gap. And finally, as the outlook, we will have to look at neutral excitations on other systems. So thank you so much for your attention.
Thank you very much, Vitali, for this nice presentation. So there's time for questions. So if you have questions, please go to the reactions part and raise your hand. I see there's a question. Claudia wants to ask a question, so please go ahead.
Okay. I have a question when you define your excited state. There is not the risk that you go down to the ground state when you define your wave function. So I know that you try to pose asymmetries, but there are some cases where it can be strange. You can have the same symmetry of the ground state or something like this.
That's exactly. It's a very good point. I sort of didn't mention it, but I put this phrase here. Indeed, it can. And for carbon, we sort of impose this symmetry by looking at the indirect gap. When you look at the indirect gap, you kind of certain that you will not go to the ground state. When you look at the direct gap, things are more not clear. In the case of hydrogen, it's a bit more simple because the ground state is just like an S state, right? So it doesn't have any nodes. Then when we excite, we sort of introduce a node, just like a sort of anti-bonding, and so there shouldn't be any problem with the orthogonalization. But you are absolutely right that in some cases we can go to the ground state. However, we have never seen this because also, for example, for carbon, we tried the direct excitation and it didn't fall into the ground state. So I know that it can exist, but I mean, personally, I didn't have experienced this fact.
Okay, thanks. I had a question about the scaling. So it seems like there are only two options in what you present. So either as 1 over L or basically as 1 over L cube.
1 over
N
cube.
Possibilities. I'm also asking because when I did some calculation just on simple Madelung constants, we found that the scaling of 1 over L squared was the best, that made the best fit at least.
Yes, there are other possibilities. There are other cases. Here we're just discussing the sort of leading terms and the gaps. The gaps well, really ongoing discussion is whether it's 1 over L or 1 over L cube. I think then, and this is also for the 3D system, right? For the 2D system, there are other scalings also on the gap.
And so maybe as a follow-up, so how are these? So you say that there's discussion about it. So I guess it's not clear and not so easy. Is
yeah.
it based on like physical arguments or just by fitting to a power law and then you know, seeing which coefficient fits the best?
Okay, this on the fundamental gap, it's more sort of clear. No, what's here? What's here? Yes. This can be shown formally, and already that fact that it's proportional to the Madelung constant. We know that the Madelung constant scales as linear system size. So here it can be shown formally. Then for the optical gap, you can also show that the structure factor, you can show formally that the structure factor will vanish. So it means that you will have the same. So it means that on the gap, you will not have any size effects. So in this, you can show formally. So it's not just a fitting.
Okay.
Yeah. So for example, this expression here, this can be obtained. You can derive it.
Okay. Okay.
And then of course we can see that in fact when we do the simulations, it doesn't go to 0. So, and in fact it sort of goes this line here. It's actually 1 over the dielectric constant. So if we sum the two extrapolations, it sort of gives us this horizontal line. But yeah, this expression is exact.
Okay, thanks. So I think there was the 2 questions. I think Rex was first. So please go ahead, Rex.
Yeah, I noticed that some of your QMC data points have error bars shown on the graph. What errors are you trying to include there, and how do you get the error bar?
So this is the statistical error bar. It's just because the Monte Carlo sampling is the just due to the Monte Carlo sampling statistical error bar.
Okay, so it's not the total error, including error in the method, for example.
No. It's just, no. This is just a statistical error. It's not the system. Yeah, no systematic. If
you wanted to estimate errors in a band gap, let's say, coming from the use of a single determinant rather than multi-determinant, is that easy to do?
Okay, that's a good question. I don't really know. How would you go about it? It will be definitely systematic error. I mean, not statistical. And yeah.
Okay, I mean, to give a concrete example, let's take your calculation where you needed to use multi-determinant wave functions. How did you decide how many determinants needed to be added together?
Okay, this is actually okay. In the case, I mean, we never did the multi-determinant expansion. We just sort of showed that in the case of multi-determinant, there will be no size corrections. Okay, no, I'm actually lying. We did try the multi-determinant here. In the case of carbon, we didn't get any reduction, so we didn't get any effect of using the multi-determinant. So I think because we didn't include enough excitations. So then simply including more excitations probably eventually will localize our excitation and will give some effect, but I wouldn't know how to estimate like how many determinants do we need. Yeah.
Thank you.
Okay, thanks. There's another question by Valerio.
Yes, thank you, very nice talk. I was quite confused about the result, your let's say conclusion, your claims about the results, the final results on hydrogen. So if you, yeah, here, for example,
Yeah.
so, but when you, for example, when you claim, so when you claim that the binding energy of Bethe-Salpeter GW and QMC agree, you're comparing the quasi-particle size corrected and the in QMC the size corrected with the non-size corrected.
With vertical non-size corrected, and this is because we know that.
Yeah, of course. Okay. But I mean, so is the difference between the size and not size corrected, which agrees with the GW and Bethe-Salpeter?
Okay, so maybe it's a bit misleading the legend here, but what I wanted to show is that actually in the low density, we don't have any size effects on the neutral gap because our excitation is well localized within the cell.
Okay.
So we can safely use the non-size corrected, or even we can look at the in the other basis, right, where we localize in a localized basis, which is giving the same number.
Okay.
And in this case, yes, the binding energy will be the difference between this quasi-particle size corrected and this red triangle, which is the neutral, which non-size corrected, but it doesn't have size effects. Okay.
Okay. I have just another question. Can you say anything about this QMC neutral or quasi-particle gaps? So on the energy, you can always say that QMC are an upper bound of the real excited energy. And about this band or neutral gap, what can you conclude? Can you say something about this, which is an important point of QMC, of course?
Okay. Well, I think if you have a good excited state wave function that's not falling into the ground state, it should be also bound by the this excited state energy, right?
Sorry, I was not listening to you because I had a phone call. Sorry.
So what I'm saying is that if you have a good wave function, which is not falling into the ground state, right? So it's orthogonal to the ground state. The QMC should give you the lowest energy within this symmetry, which will be the symmetry of the excited state. So if you have, then it means that you will have the lowest energy for the excited state.
Yeah, but I mean, you're making a difference between energies that should both be upper bounds. But
exactly.
Yes.
So in principle, if they all you have the upper bound for the excited state, for the ground state, so you.
But
I don't know how exactly they will go into this bounds, right? How in the whether they will go into this bounds in the same way or not, but in principle they should be bound by the exact excited and ground states.
Okay, thank you.
Okay, thanks. So maybe just a clarification for me. So just to be sure that I understood. So when you say that you do not put, that you have no size corrections, but the results that you show in the graph, they are still extrapolated results?
No.
Just for the biggest simulation cell that you have.
Exactly, yeah. So for the case of hydrogen, it's just for the biggest simulation cell that I have. Yeah, exactly.
Okay.
That's because the here for this case of the lowest density, I think is the safest, right? Here we really see also from the Bethe-Salpeter result that the excitation is well localized. So the exciton is well localized within our cells. So we can have this conclusion that there will be no size effects on the neutral gap.
Okay, because again, I can understand that you want that. Okay, if the exciton is well localized in the simulation cell, that is crucial, but there could be other effects that's due to the finite size of the simulation cell. Not that.
But this would be these effects should in principle cancel with the effects on the ground state itself, the ground state energy itself. So you have some size scaling of the ground state energy, which is usually 1/n.
You should cancel in the infinite limit. But if you have two, I mean, I would guess that if you have two very small simulation cells, that the neutral gap in those, I mean, sufficiently big to have the exciton inside, but that they will not give exactly the same results for the neutral gap, right?
Probably not. Probably not if they are too small. Maybe there will be some other size effects entering. But in principle, if you have the same scaling of the excited state as of the ground state for the gap, they should cancel each other. There can be some other beyond leading order effects that needs to be included. Just like it was the case for the fundamental gap, for the slowest simulation cell, we had to also include some other effects that were 1/n actually, 1 over number of electrons. So it can be true what you say that for the lowest, for the very small simulation cell, there will be some other effects entering.
Okay. Okay, thank you very much.
Thank you so much.
I don't see any other questions, so maybe this is a good point to stop here. So thanks again, Vitaly, for the nice presentations. Thanks to everybody for joining and for the questions.
Thank you for the invitation.
Maybe see you next time.
Thank you.
Thanks very much.
Bye-bye.